Dear students, today's topic is the Coulomb gauge and Lorentz gauge. Topic code is EMPF-S3. First we take the Coulomb gauge. Typically what the bottom line here we will achieve that is magnetic vector potential is expressed in terms of U. So as in magnetostatics we pick the divergence of A is equal to 0, equation number 1 we take, and also for Poisson equation we take the electrostatics the del square of U is equal to minus rho by epsilon naught for free space. This equation number 2. But one does not has to be deceived, though unlike electrostatics U by itself does not tell us about E, as we have to know A as well. Now refer to this equation, which is E is equal to minus gradient of U minus delta A by delta T in electrodynamics. See, the solution of Poisson equation corresponds to the U is equal to 1 over 4 pi epsilon naught the rho time rho by R, 1 over R. The charge density is distribution and by R over the integrated over the whole volume V. Call this equation number 4. There is a strange thing about the equation 4. It says that the potential everywhere is determined by the distribution of charge. Right now, if an electron is moved, suppose now if an electron is moved in the lab, the potential U on the moon instantaneously record this charge. This sounds particularly odd in view of the relativity, which allows no messenger to travel faster than the speed of light. Now the point is that U by the scalar potential U by itself is not physically measurable quantity. At the moon one can measure E, and that involves A as well. So somehow it is built in to the vector potential in the Coulomb gauge that whereas the U instantaneously reflects all changes in rho. So the combination which we get the minus gradient of U minus delta A by delta T does not. So E will change only after sufficient time. Sufficient time has lapsed or passed for the news to arrive. Now the advantage of the Coulomb gauge is that scalar potential is particularly simple to calculate. The disadvantage, apart from the non-casual appearance of the U mentioned above, is that A is particularly difficult to calculate. The differential equation for A is given as del square of A minus epsilon naught mu naught delta 2, that is delta 2 by the A by delta T square is equal to minus mu naught J plus epsilon naught mu naught gradient of delta U by delta T, where the gradient of divergence of A is equal to 0. So hence A is expressed in terms of U. In this case the A is expressed in terms of here the U, which is the two physical quantities which are linking that event in the lab and observer at the moon. So that is the in the Coulomb gauge, the A delta 2 the del square of A minus epsilon naught mu naught delta 2 A by delta T square magnetic vector potential is now corresponding with the scalar potential U, and that is the main conclusion for that. So A is expressed in terms of U. Now in Lorentz gauge, here the concluding bottom line is that the A and U are treated are gauged on equal footings. In Lorentz gauge we pick the divergence of A is equal to minus epsilon naught mu naught delta u by delta t is equation number 1. This is established to eliminate the last term at the left hand side in the below equation, which we have already the gauge transformation we have developed. Del square of a is equal to del square of a minus epsilon mu naught del square of a by t minus gradient of divergence of a plus epsilon naught mu naught delta u by delta t is equal to minus mu naught j. Call equation number 2. Since now this whole term, in this term we have the divergence of a plus epsilon naught mu naught delta u by delta t is equal to 0 with the gradient obviously. So what we get, the divergence of, from this expression we get the ignoring the constant and integrating the both sides, but the divergence of a plus epsilon naught mu naught delta u by delta t is equal to 0. So constant may be equal to term as equal to 0. Divergence of, hence divergence of a is equal to minus epsilon naught mu naught delta u by delta t. So if you put here the divergence of a value, the in this case will be the mu naught minus epsilon naught mu naught we get from this whole term is the minus mu naught epsilon naught delta u by delta t. So we have equation 2 written as the when we put that here, we term, this whole term is equal to 0. Here the divergence of a1 is equal to this term, that these the two difference will be equal to 0. So we will have del square of a minus epsilon naught mu naught delta 2a by delta t square is equal to mu naught j. So meanwhile the Poisson, the equation for the potential u in Poisson equation will take the form by putting the divergence of a is equal to minus epsilon naught mu naught delta u by delta t as delta square of u del square of u minus epsilon naught mu naught del square of u by delta t square is equal to minus rho by epsilon naught. So the what we have, the term Poisson equation wrote that the del square of u plus delta by delta t divergence of a is equal to minus rho by epsilon naught. So the Lorentz gauge, the expressed as the special virtue of the Lorentz gauge is that it treats the potentials u and a on equal footings. The same differential operator in 4 dimension is given as del square minus epsilon mu naught del square by delta t square. We now call the 4-dimensional operator. These are 4 sides. So this is the now Laplacian is now expressed in terms of the now the 4-dimensional operator. This is the quad square, or this is a delta. So the del square is a quad square, or is called D'Alembertian operator. D'Alembertian. Now the democratic treatment of the u and a is particularly nice in this in the context of the special theory of relativity, where D'Alembertian plays the same role with what the same role as the Laplacian or the Poisson operator here have in classical physics. So we will be using this D'Alembertian instead of the Laplacian or Poisson operator in electrodynamics, relativistics, the field where the fields are the dimensions, are the speeds are relativistics. Then D'Alembertian operators are used. So the quad square D'Alembertian square a is equal to minus mu naught j is equation number 6, and del square the quad square u D'Alembertian square of the scalar potential is equal to minus 1 over epsilon naught rho. Equation, this is number 7. So equations 6 and 7 are regarded as 4-dimensional forms of Ampere's law, and this is the Ampere's law and this is the Poisson equation respectively in electrodynamics. We take in this form. So in Lorentz, what we got, that the Lorentz gauge, we have, this is the main bottom line, that it treats the potential u and a on equal footings. Here that is the u and A are the treated to be on the equal footings. So what we have here we have the del square of equally the same footings as we take the u. Okay, so on both sides you can see the same expressions we get. um, the del square of u minus epsilon mu naught del square delta 2 by delta u delta 2u by delta t square. Similarly the same, it treats the both potential on the equal footing. So the two equations on the left hand side. The right hand side is obviously the consequence of the Ampere's law, and this is the Gauss's law. So they have the the treatment is on the equal footing. Okay, with this we reach to the end of the topic. Thank you very much.